Okay, so we're going to go through logarithms, and I guess specifically this is the power law for logarithms. I guess I should write that on the side there, so we have that idea. Power law. Okay, so power law of logarithms. Now this is important to keep in mind. Is this is a basic conversion law that, and usually it's easier to start with the exponent. If we have a value equal to some base to y as the exponent, we can convert that to a log where the part that it's equal to becomes a log to the base that we had before of that value, and the exponent becomes what it is equal to. And this will help us solve for quite a few exponential functions where we're unsure what the exponent is equal to. And this one is just another one that helps us to convert things to base 10 log because of our calculators pretty much only being used, or most of the ones we'll have only have base 10. This is a way to solve values when we have a log that's not base 10. Okay, so first one we have here, what is the question? It just asks us to evaluate such a thing. So what we're going to do is we're going to kind of color code this. Now we know that we can bring down this 3. This power of 3 can essentially come down in front of the log. So what this will read is 3 log 2 to 16. So we have to figure out how to convert that, and that we're going to use way up here to figure out. Okay, we're going to go back and use its conversion. So we'll color code everything we have. So our x value in the log is our 16. Our base is 2, and our 3 is unknown, right? We don't actually, in our example, have a value at this point. We can call it something. In fact, I'll give it a variable. Let's call it, oh, I don't know, z. Okay. This z is technically the same idea as the power of the x here. Okay, so our 3 is our z in this case. So if we're going to convert this to exponents here, if we're going to convert this to an exponent, our base is 2, okay? So we have a base of 2, just like our base above. Our y value, which is what this is equal to, oh, we don't have a value for it right now, so it's an unknown. I shouldn't call it x, I should call it y. Is equal to, what else information do we have? Well, we have the green. This becomes what this is equal to. So our x value is what the exponent is equal to. So it being 16, 16 is what it is equal to, and to the power of 3. Okay, so we have the power of 3 here. In this case, in terms of our evaluation, oh, sorry. I thought they wanted us to convert. This is fine. We can use this as a conversion and work from here, or technically what we should have used to solve this, because of our base, we should have used this rule here, where we had to log 2 base 16, okay? And what we could have done there is we could have brought the 3 down and then used it as a coefficient over here. We convert it, nothing wrong with that, and we could use some exponent rules to go ahead solving this, but logs are usually the fastest way to solve it. Come here, you. Okay, so let's actually convert it. Sorry, let's actually put it into where we were supposed to put it into. So our log base m, okay? So this would have been our base in that case, and this would have been our m value. Again, the 3 comes down in front, like we said before, and that 3 would fall into this part. So if we were to convert it to 2 logs, we'd have log 16 over log our base 2. So log base 10 is 16 to log base 10, 2, and technically our coefficients multiply by 3. So we can put this into our calculator to help us evaluate. I thought I actually said convert at first. So our 16 log base 10 divided by 2 log base 10 is equal to, okay, and then times 3 gives us a value of 12. So when we evaluate this, we get a value of 12. And we could have probably seen this in our exponents if we had plugged in, if we evaluate what 16 to the power of 3 is, might as well, since we converted it. 16 to the cubed is 4,096. And let's put 2 to the power of 12, because that's what we found, 4,096. So that's exactly what it was. So we use this, which is what we should have done, because it wasn't a conversion question, to help us solve our logs. Okay, so with that being said, our second example, we need to figure out what this power is equal to. And one of the ways we can do this is put these to a base. We can find the logs of both sides. So what we're going to do is going to find the log base 10 of 10 is equal to the log base 10 of 4 to the power of t. I guess I should fix that g there. Okay. And the reason we do that is because we can now bring down that exponent, right? Okay. And when we bring that exponent down, we have log base 10 of 10 is equal to t times log base 10 of 4. Well, we can now isolate for b because t says this, or this part of this says t times log 4. So we bring log 4 over, and we end up with log base 10 over 10 divided by log base 10 of 4. And this part we can just use a calculator to evaluate, same idea. So if we have our 10, log base 10 is 1, divided by 4 log base 10 is equal to 1.6609. So we'll round it to 1.66, approximation, and we can test it, right? If we put 4 to this power, it should give us roughly 10. It probably won't be exact because we rounded our value, but 4 to the power of 1.66 gives us, 9.98. And if we were more accurate, we would have got exactly 10 when going through that part. Okay, finally, in our last example here, we have an investment. Somebody's putting in $500 into an account, and this account's earning 7%. And maybe it's every year. That's what T stands for, is our time in years. What we want to figure out are two parts of this. We want to figure out when this will double and triple. Okay? So, if we start with $500 in their account, and this is our original principal, this value here, what would be a doubling of this?
1,000.
1,000, exactly. So in other words, that's our new A at T. A at T being our total amount in the end. This is our amount after a certain amount of time. So we're looking to solve when this is equal to 1,000, okay? Equal to 500, 1.07 to the power of t. And this will make sense in terms of doubling because one way we can simplify this is by bringing 500 over. So when we bring 500 over, we'll divide by 500. And what is 1,000 divided by 500?
2.
2. And 2 is the idea of doubling, right? So 2 is equal to 1.07 to the power of t. This ends up being very similar to what we did before. We find the logs of both sides. So we find log base 10 of the value of 2. And log base 10 of 1.07, the power of t. We know from here, t can come down in front of our log. So we'll have log base 10 2 is equal to t multiplied by log base 10 of 1.07. And then we need to move 1.07 to the other side. Log of 1.07, and that will give us our t value, so how much time it'll eventually take. Same idea, we take our logs, so 2 base 10 divided by 1.07 base 10 is equal to 10.24. Okay, 10.24. So, and we can use that to check. We take our 1.07 and put it to this power. Check our answer here. 1.07 to the power of 10.24 is equal to 1.999, which is essentially our 2. The second part of the question asks us to triple it. And tripling it, we can figure that out pretty quickly by multiplying this by 3. But if we noticed, this is all kind of redundant. The goal is to get to this part. And if doubling represented 2, if I were to start the question from here, what value would I have on this side of the equation?
3.
Yeah, exactly. So we can start right there with the value of 3 and run through the exact same process, 1.07t. We already know by kind of looking at this, so I'm going to jump ahead, that this question is going to end up reading log base 10 3 divided by log base 10 of 1.07. That will equal t. If you're kind of confused, it's just essentially what we did on this side. And we'll run the same numbers to figure out how much longer it's going to take. 3 base 10 divided by 1.07 base 10 is equal to 16.23.